Hello everyone, I'm Alejandro, owner of Tutoring by Alejandro, and a viewer requested that I make a video on MCAT physics, okay? So I brought some physics exercises that we'll tackle together, okay? So this one is about projectile motion, and it reads, a ball is launched from level ground with speed v naught, or initial velocity, equals 20 meters per second at an angle theta equals 37 degrees above the horizontal. Neglect air resistance. So A, determine the total time of flight. B, determine the horizontal range. C, determine the maximum height. So we'll use G, being the acceleration of gravity, as 10 meters per second square. Sine of 37 degrees approximately equals 0.60, and cosine of 37 degrees approximately equals 0.80. So what we want to do is we want to first split the initial velocity into its horizontal and vertical components because they do behave differently. Okay, this is necessary because horizontal motion has no acceleration, okay, it's constant velocity, while vertical motion is accelerated downward by gravity, okay? Hence, the graph you see on the left, right? And, since it's accelerated downward, we take downward as a convention as a negative value, okay? That's why you see the negative g there, okay? So the horizontal component comes from the cosine, and the vertical component comes from the sine. And I'll show you how to break that down, okay? So we need to use a little bit of trigonometry to do this, okay? If you remember a right triangle, okay, let's do that. Right, we have our angle theta, right? Okay, so for the hypotenuse, we have initial velocity. The vertical component is v naught y, and the horizontal is v naught x, okay? So we'll use what we learned in trigonometry to solve for each of them. So for the sine of theta is equal to the opposite side to the angle, which is v naught y, okay, divided by the hypotenuse, which is v naught, okay? So we're going to solve for v naught y, okay? So what we want to do is we want to multiply both sides by v naught, okay? And that will give us v naught y is equal to v naught times sine of theta. Okay, great. So we're going to do something very similar with v naught x, the horizontal component of the velocity, but we're going to use cosine. So cosine is equal to, this time, the adjacent side, right? So it's going to be equal to v naught x, right? So we're going to write that, v naught x, divided by the hypotenuse, okay? Again, it's going to be v naught, the initial velocity, okay? And similar to v naught y, we're going to solve for v naught x. It's going to have a very similar structure. It's going to be v naught x equals v naught, initial velocity, times cosine of theta, okay? So now we have our two equations that break down the velocity in terms of horizontal and vertical components, okay? And we can start calculating some values, right? Okay. We know that the initial velocity is equal to 20 meters per second, right? Okay, so let's solve for v naught y. Okay, v naught y is going to be equal to 20 meters per second initial velocity times the sine of theta, right? So we know that the sine of 37 degrees is approximately equal to 0.60. Okay, there we go. So let's multiply that. 20 times 0.60 is going to give me 120. Oops, sorry, I mean 12 meters per second. Okay, so that's our vertical component of the velocity, v naught y. Okay, in a similar way, we'll calculate v naught x. Okay, v naught x is equal to, again, the initial velocity, 20 meters per second, multiplied by, this time, the cosine of theta. Cosine of 37 degrees is approximately equal to 0.80. Okay, we're going to multiply them. All right, so we have 20 times 0.80, and that's going to be 16 meters per second. Okay, great. We have both components of the velocity, right? So now we have to calculate the time of flight. Okay, so for the total flight time, we're going to use the vertical displacement equation. Okay, so you don't have to memorize all the equations in the MCAT, but this one is a pretty useful one. Okay, so we have y of t equals v naught y, the initial velocity in the vertical component, times t, the time. Okay, minus, because remember the direction of the acceleration in this case is downward, right? We're taking it as a negative, so negative 1/2, okay, times g, which is our acceleration, times t squared. And y of t is just our vertical position at any point in time, right? Okay, so at launch and landing, the height is the same, right? We launch the ball from a height of 0, and when it touches the floor again, right? You know, the time of flight, right? At the end, y is also going to be equal to 0. Okay, so let's substitute that for 0. Okay, great. And we're going to factor out t. Okay, so let's see what that gives us. Okay, that is going to be, 1 second, common factor t. We're going to use common factor t. So it's 0 equals t common factor, so open parentheses, v naught y, okay, minus 1/2 of g, and then we have the t left over since it was t squared, right? Right, so you see two terms here. You have a t multiplied by those terms inside the parentheses. So we're going to have two solutions, right? So there are 2 points in time where the height is equal to 0, where we first launch the ball and when it hits the ground again, right? So our first solution, t equals 0, that's not very useful. So what we want is the second term, right? So we're going to set the second term equal to 0, and we're going to solve for t. So v naught y minus 1/2 g times t is equal to 0. Okay, let's solve for t. Okay, just got to do a little algebra here. We can add both sides of the equation by 1/2 g times t. Okay, so that cancels out the negative 1/2 gt on the left, and it leaves us with 1/2 gt on the right. Okay, next we're gonna multiply both sides of the equation by 2. Okay, that leaves us with gt on the right. Okay, and finally we will divide both sides of the equation by g. Okay, so that's going to give us t is equal to 2 times the initial velocity of the vertical component divided by g, the acceleration of gravity. Okay, so let's substitute the values we know. We know v naught y is equal to 12 meters per second, okay, divided by g. G is 10 meters per second squared. Okay, great. Let's see how the units end up. 1 second. We can cancel meters with meters, right? And then we can cancel out one of the s's of the s squared, right, with the seconds in the numerator, right? So that means that our final units are going to be seconds, which is what we want. So if you're solving this and you get anything other than seconds, then just go back and see if you made a mistake. All right, so calculating will give us, let's see, we have 2 times 12 divided by 10 equals 2.4 seconds. Okay, so the total flight time is 2.4 seconds. That's the time the ball takes from being thrown to hitting the ground. Okay, so now we need to find the horizontal range. Okay, so now remember the horizontal component of the velocity has no acceleration. It's a constant velocity. So we can use some of the basic equations you learned in the beginning of physics, right? Namely, a velocity equals distance over time, right? That's going to help us in this case because there is no acceleration, right? So we can reaccommodate this to our case. Instead of v, we're going to write v naught x, right? Instead of x, we're going to write r, being the range. That's the horizontal range, and divided by t, okay? It's pretty much analogous. We're going to solve for r, so we just multiply by t on both sides, and that gives us r equals v naught x times t, okay? And we do know both values, right? We know v naught x is 16 meters per second, okay? And we know that the time is 2.4 seconds, okay? So solving for r gives us, oh, and canceling the units, right? We want to end up with meters, right? Because horizontal range is a unit of distance. Okay, good. That gives us 16 times 2.4. 1 second. That gives us 38.4 meters. Okay. All right. So that is the horizontal range, 38.4 meters. Okay. So if you want to verify, that 38.4 meters, there is a way of obtaining what we call the closed form range formula, okay, using the r equals v naught x times t, okay? So just as a reminder, the t that we calculated was equal to 2 v naught y over g, right? Okay, because we're going to use that for the closed form range formula. Okay. We also know v naught x. Remember, v naught x is equal to v naught times cosine of theta. That's going to be useful as well. Okay. So let's see what that gives us. Okay. So we have r equals v naught x times t, right? R is equal to, we know that v naught x is equal to v naught times cosine of theta, right? Okay, great. And then time. Instead of t, we're going to write 2 times v naught y over g, right? And at the same time, we know that v naught y is equal to v naught times sine of theta, okay? All right. So if we plug everything in there, we will get 38.4. And the cool thing about this is that we can use what was given to us in the beginning, from the beginning, right? And just plug everything in and obtain the range without doing, any further mathematical manipulation. That's if you know how to derive this or memorize this somehow, right? But nonetheless, it is useful for making sure you got the right answer, okay? Okay, great. So now we have to determine the maximum height, okay? So at the top, whenever you throw an object, right, vertically, it sort of, stops. It sort of pauses for a brief moment in time. So the vertical velocity at the top is 0, okay? Right? So we can derive this formula that we're going to use in 2 ways, right? So we're going to use kinematics first. So we have vy, the velocity of at any point in time, squared equals the initial squared, okay, plus 2 times the acceleration times the difference in position. So x being the position at any point in time, and x naught being the position, the initial, right, position. Okay, so let's adapt this to what we have, right, since we're dealing with vertical motion, right? capital H is the height difference, right, between the position where you throw it at, which is 0, right, and at the top, right? So what we're going to do is we're going to replace x minus x naught. We're going to replace that by our capital H, which is what we're going to try to calculate, right? That's the maximum height. Okay, H, capital H. Okay, what else? So A is the acceleration. At this moment, we're dealing with vertical velocity, right? So our acceleration is gravity, right? And so remember, since the gravity is pulling the ball towards the earth, it's going downward, so it's a negative, right? Remember, the acceleration has a directional component. In this case, it's negative. So we have negative 2g times h, okay? What else? As I mentioned earlier, so when you throw something up, when it reaches the top, it's going to pause for a brief moment, okay? So we're going to set Vy squared equal to 0, right? The moment where it reaches the top, it's going to pause, okay? That velocity there is 0. Okay, and we can solve for the maximum height. Okay, we can add 2gh on both sides. That'll give us 2gh equals v naught y squared. Okay, then we can just divide, by the 2 times g on both sides. Oops, okay, great. So h is going to equal v naught y squared, okay, divided by 2 times g. Okay, great. And okay, that is going to be equal to, we know v naught y is equal to 12 meters per second. And remember, this is squared. Then divided by 2 times g, which we know it's 10 meters per second squared. Okay. So at the top, right, the numerator, we have to distribute the squared, right, to both the meters and the seconds, right? So in reality, you have 12 squared meters squared divided by seconds squared. And those seconds squared in the numerator will cancel with the denominator's seconds squared. Okay? And then one of the meters from the numerator will cancel with the meters in the denominator, leaving only units of meters, right? Okay, so let's calculate this. We have 12 squared is 144 divided by 20, right? 2 times 10. And remember our units are meters, right? That's what we're left with. Okay, then calculating that will give us 7.2 meters. Okay, so that is the maximum height that the ball reaches. Okay, so you see that right there in the graph, 7.2 meters. Okay, so I mentioned that there are 2 ways we can obtain the height. We used our kinematics equations, right, to obtain that. But we can also use energy, right? So at launch, the ball has vertical kinetic energy, and at the top, that energy is fully converted into gravitational potential energy. Okay, that's the principle of energy conservation. Okay, so we can use that in order to calculate H as well. Let's say for some reason you forgot the kinematics equation, but you remember the principle of energy conservation. So we will use that, and that is 1/2 times, okay, m being the mass of the object, okay, times v naught y squared, initial velocity in the vertical component squared. That is our kinetic energy, right? And our energy is conserved, so that is going to equal m mass g, gravity, right, times r h, right? That's the height, right? And that is potential energy, because at that moment in time, it's not moving, right? And they're equal to each other due to the principles of energy conservation. Okay, we're going to cancel the m's, okay, because we have m on both sides. Now we have 1/2 v naught y squared equals gh. Let's divide by g on both sides, and that gives us h is equal to v naught y squared divided by 2g. Okay, so we ended up with the same equation, so we'll get the same result regardless of which path you take. Maximum height at the end of the day is going to equal 7.2 meters. Okay, so to summarize, the time of flight is equal to 2.4 seconds. The range is 38.4 meters. The maximum height is 7.2 meters. We saw some kinematics equations. We even saw some energy principles. You don't have to, memorize them. You can rebuild them on the spot as long as you understand the fundamentals. So if this was helpful, like, share, comment, subscribe, and I'll see you guys in the next video. Bye-bye.